Section 2.3, Graphs that Enlighten and Graphs that Deceive. Key concept, we're going to introduce some other common graphs that foster understanding of the data. And we're going to discuss some graphs that are deceptive because they create impressions about data that are somehow misleading or wrong. Technology now provides us with powerful tools for generating a wide variety of graphs. A dot plot. This is a graph of quantitative data, looks similar to a histogram, in which each data value is plotted as a point or a dot above a horizontal scale of values. Dots representing equal values are stacked. The features of a dot plot: it displays the shape of the distribution as we saw with the histogram. It's usually possible to recreate the entire original list of data values. We can also do a stem and leaf or a stem plot, and this also is used for quantitative data, and it separates each value into two parts: the stem, which is the leftmost digit, and the leaf, which is the rightmost digit. So here's a stem and leaf for pulse rates, and if we notice at the top of the diagram we have one stem number, which is 40, and we have two leaves, so the pulse rates there are 40 and 42. We continue down, the next to the last line in the stem plot is 90, and then we have a 90, a 92, a 94, and notice if there's duplicates in the data set, we put two leaves there, so there's two 96 values, so we have two leaves of 6. Features of a stem plot, again, shows the shape of the distribution and also retains the original values, and also the data are sorted, arranged in order. A time series is where we have quantitative data that have been collected at different points in time, like over months or years, and we plot along the x-axis the time variable, and we can see patterns perhaps that we wouldn't see in the data if we just did a histogram or a stem and leaf or a dot plot. Features of the time series reveals the information about trends over time. Bar graphs is a graph of bars of equal width that show the frequencies of categorical data, and we have gaps between the bars in a bar graph. They show the relative distribution of the categorical data, so it's easier to compare different categories. A Pareto chart is a bar graph for categorical data with a stipulation that the bars are arranged in descending order according to the frequency, so the bars decrease in height from left to right. Shows the relative distribution of the categorical data and also draws attention to the more important categories that will be shown on the left side of the Pareto chart. So here's a Pareto chart of stolen boats. And we notice our eyes drawn to the jet ski, which has the highest frequency, followed by the motorboat, utility, inboard, and finally sailboats. Pie charts or pie graphs are a very common way to depict categorical data as slices of the pie, where we want to look at how the parts relate to the whole. They show the distribution of categorical data in a commonly used format. Here's a pie chart for that data that we just saw in the Pareto chart. A frequency polygon uses line segments connected to points located directly above the class midpoint. A frequency polygon is similar to a histogram, but it uses line segments instead of the bars. And we can also do a relative frequency polygon. So here's an example with that lunch data that we had in the last section. And basically what happens is you remove the bars of the histogram and simply show the frequencies or the relative frequencies with a dot, and they're connected, and they always start at the x-axis, go up, down, whatever happens, and then they always end up going back down at the y-axis to 0. I'm sorry, on the x-axis at the highest point back down to 0. And here's the McDonald's versus the Dunkin' Donuts relative frequency polygon shown on the same graph, so we can see nice comparison between the two groups. Graphs that deceive. A non-zero vertical axis. This is a common deceptive strategy that's used to exaggerate differences between groups. So for instance, if we look at this graph here, we're looking at the number or percent of people experiencing nausea who took OxyContin or a placebo. And if you notice on the y-axis, it starts at 10% rather than 0%. So the difference between the two groups is really exaggerated here. If we actually took the y-axis from 0, we'd see that the difference between the two groups is it's still great, it's still large, but not quite as large as the left graph would imply. Drawings of objects called pictograms are often misleading. The data are one-dimensional in nature, but they're often depicted with two-dimensional items. And by using the pictogram, the artist can create false impressions that grossly distort the differences with simple principles of geometry. If you double each side of a square, the area doesn't merely double, it increases by a factor of 4. If you double each side of a cube, the volume doesn't just double, it increases by a factor of 8. And here's an example here. If we look at this pictogram for the percent of adults in the United States who smoked, in 1970 it was 37%, and in 2013 it was 18%. If we notice the cigarette, it increased in two dimensions, the width and the length. In addition to the graphs we've discussed in this section, there are many other useful graphs, some of which have not even been created yet. The world needs more people who can create original graphs that enlighten us about the nature of data. Concluding thoughts. In the visual display of quantitative data, Edward Tufte offered these principles. For a small data set of 20 or fewer values, use a table instead of a graph. A graph of the data should make us focus on the true nature of the data, not the other elements such as eye-catching but distracting design features. Do not distort the data. Construct a graph to reveal the true nature of the data. Almost all the ink in the graph should be used for the data, not for the other design elements. So let's take a look at some data here. So here we have platelet counts collected from a group of adults in the United States. Why does it not make sense to construct a histogram for this data set? Well, it's a really small data set. And remember, Tufte just said if you had less than 20 data values, you want to just really look at the data. So it's so small that we really can't see the true nature of the distribution with such a small sample size. The weights of 10 randomly selected puppies recently born in a large kennel are shown below. Create a dot plot of the weights. So I've given you 3 dot plots, and I want you to figure out which one would be the correct dot plot. So you want to look at the data, and you want to see what we see in the graphs. We notice that graph C is different than the other 2 graphs, that the lowest value shown here is a 10. And if I look at my data, I don't have any value in the data less than 10, so I can eliminate C. And I do have a value of data of 10 in the data set, so that's shown here. I've got 2 values of 12, that's correct. And then it looks like a 13. And then do I have a value of 14 in my data set? I do, right here. So it looks like B is going to be the correct answer. And then 3 18s and 1 19. Graph A shows a value at 17, which does not appear in the data set, so the correct dot plot is B. 10 test scores from a recent exam are listed below. Create a stem and leaf. So the first thing you want to do when you're going to do that is put the data values in ascending order. And I'm going to give you 3 choices to pick from. So if I look here, I have a 55, and I see that as the top of each of the stem and leaf diagrams. And then I have a 67 and a 69, and I see a 67 and a 69 here. Here I see a 64, which I don't have, so I can eliminate B. And then let's keep going. I've got a 74, which again I don't see in B, which I've already eliminated. And then I've got an 82, an 83, an 88, and 89. 82, 83, 88, and 89. 82, 83, 88, and 89. And then I have a 91 and a 93, which I see in stem and leaf A, but not in stem and leaf C. So A is the correct answer. How does the stem and leaf show the distribution of the data? So what does it tell us? The lengths of the rows are actually going to be what? Relative, the same thing as the height of the bars in the histogram. So the correct answer here is A. The lengths of the rows are similar to the heights of the bars in the histogram. Longer rows of data correspond to higher frequencies, and we see that with the 8. That's the highest frequency. A random group of 10 students were asked about their favorite color. 5 said red, 4 said green, 8 said blue, 2 said yellow, and 1 said purple. All right, so the first thing you want to look at for a Pareto is you're going to have the highest frequency on the left side. So it looks like blue followed by red, followed by green, followed by yellow, and then purple. And I've given you 4 choices here. So let's take a look. So we see blue here as the left one, which is not correct, is it? Because that should be it should be blue, but I don't, is that correct? Yeah, these are relative frequencies, by the way. So I've got blue, and then I said green, and then purple. Well, no, see, this is not a Pareto because it's not in descending order. So it's going to have to be C, right? Because look at this, blue, red, what did I say? Blue, red, green, yellow, purple. The correct graph is C. Why is this graph deceptive? In a survey of adults, subjects were asked if they felt comfortable being in a self-driving vehicle. The accompanying graph depicts the results based on data from TE connectivity. Why is it deceptive? Look at that y-axis. Okay, it starts at 200 rather than 0. It also is exaggerating the difference between the yes and no answers. It appears to be 5 times larger when it's actually only about 2.5 times larger. And there are other resources for you for this section. There are 2 StatCrunch videos available in my courses. One shows bar graphs, Pareto charts, etc., and the other shows dot plot, stem and leaf, and how to use StatCrunch to create those displays.